Cancer has many faces: the patients, the family members, the nurses, the doctors, the surgeons. But we hardly see the faces of the researchers who look at cancer very differently. They study cancer on the molecular and cell level. One of these researchers is Ron Hero. Ron heads a team of fundamental researchers who use high-tech equipment to study cancer cells. Fundamental research in labs such as these is at the basis of many breakthroughs in the battle against cancer. The knowledge gained is essential for applied researchers to develop less invasive and more personalized treatment. We ask Ron what his research entails.
What we're trying to research here is actually how the environment of a tumor affects tumor growth and metastasis. What happens in a tumor? A tumor is effectively cells that continue on dividing without limit. So here in black, you actually see all these tumor cells which are dividing away. So in blue, I sort of sketched the normal cells. And what's going to happen is that these tumor cells are going to start dividing and they're going to push away all these normal areas of the cells. Yeah. The center area, what you can see here, is actually deprived of some of the blood vessels. In other words, it will have a lack of supply of nutrients, it will have a lack of oxygen. So this environment is becoming low-level oxygen. It's going to be hypoxic. What's happening there? Well, these tumor cells respond to their changing environment. And what's going to happen? They're going to send out molecules. They're going to send out signaling molecules that actually change the surrounding cells and that actually change the behavior of all of these tumor cells and the surrounding cells as the cancer progresses. Let's suppose these cells here in the center become hypoxic. So they don't have any oxygen anymore, so they have to decide what their fate is going to be. Yeah, so let's say these cells are starved for oxygen. So our research focuses on trying to figure out what at these cells the local composition is. That means what the different molecules are that constitute the cells. And the different molecules right now, I'm talking about the proteins, which are the workhorses in the cell, as well as the smaller molecules, little signaling molecules that take care of the energy household of this tumor. One of the molecules that we found in our research, which is upregulated, of which the concentrations are elevated upon the absence of oxygen, is a protein which is related to cell adhesion. So cell adhesion is taken care of by proteins and other molecules that are on the outside of the cells that glue these cells together. Once these proteins are downregulated, what happens is these cells start to detach and they're going to wander about. And they're going to go. They're going to leave the main tumor mass. So at the same time, this tumor says, hey, listen, I don't have any oxygen anymore. I need more blood supply. So it's going to send out signals. So let's make these red. It's going to send out red signaling molecules to the environment, telling this healthy tissue and the blood vessels, I need more blood, I need more blood vessels. So what's going to happen? New blood vessels are going to grow. And also here, new blood vessels are going to grow. However, these new growing blood vessels are not closed yet. So effectively, they're like a leaky inner tube of a bicycle. Yeah? That leaky inner tube doesn't only let air escape, but it also provides an escape pathway of these cells that just have detached from the tumor. So what we're trying to do is actually to understand how these molecules that are sent out inside the cells and by the tumor mass itself actually affects this process of metastasis in tumors.
We followed Ron into his lab to ask him just how his research is done.
Well, one of the things we do here, we actually try to do imaging mass spectrometry. But imaging mass spectrometry starts with samples. And this lab where we are here now, that's actually where we prepare our samples. And these can be patient materials, and these are typically tumors which we try to assess. So it starts out over here, where actually we are cutting the tissues in very thin slices. Now normally in a hospital, people would stain these slices with a red and a blue color and take high-resolution imaging pictures. We also do that, but we want to move our research beyond that with the technology which is in the next room over, which are our mass spectrometers. So normally we first go here, we stain the slices, and we move to this high-resolution microscope where under the microscope we can see the individual nuclei of individual cells, and we also see the different structures in this case a tumor. However, a pathologist doesn't know what the underlying molecular signals are, and that's actually what we're trying to resolve in the next room using imaging mass spectrometry. In this lab, we are trying to use imaging mass spectrometry. So a mass spectrometer, which we're surrounded by here, is a device which weighs molecules. And by weighing the molecules, we can actually elucidate its structure. And it's very simple. If you think about a protein, has a number of amino acids. Each amino acid is like a Lego brick which has a specific mass. So we weigh all the Lego bricks together, and then we fragment it, and we measure the pieces. We paste the pieces of weight together until it sums up to an intact molecular weight, and we know what the sequence of amino acid is. So by measuring the molecular weight, we can tell something about the structure. Now, how do we go from the molecular weight and its structure of a molecule to the distribution of these molecules on the tumor tissues? Well, it's very easy. We can do this in these instruments. And the way we do that, we focus our laser beam, we fire the laser, and we evaporate a little bit of a molecule. And that molecule, when it evaporates, also becomes a charged particle. And these charged particles, they fly through these mass spectrometers, and by measuring their arrival times, we actually measure their weight. By doing mass spectrometry on each point of the tissue, which we put on these type of slides and put them in the mass spectrometer, we can actually generate these images. So point-by-point analysis, taking a mass spectrum at each single cell, or even a number of mass spectra on the different cells that constitutes the tumors that are on these slides. And then, after analyzing gigabytes and gigabytes of data, we finally figure out what the distribution of these molecular signals is throughout these tumors.
How and when are patients going to benefit from your research?
Well, effectively, that's already happening. I mean, the fundamental research, which started about 10 years ago, was very much focused on trying to understand how we can reveal these molecular signals using imaging mass spectrometry. So all this technology has developed over the last 10 years, and now people are applying these technologies in the hospital. Not to a very high level yet. In high level meaning there are no drugs developed that actually affect patients, but we can see molecular signals that will help us predict what the outcome for a patient is. So for instance, that helps with diagnosis, and in a lot of cases also with prognosis. To give you an example, if I can look at patient samples that are suffering from a particular type of cancer, this could be breast cancer, this could be colorectal cancer, I do a molecular image analysis which tells me if and how this patient will respond to chemotherapy. Then that allows the medical professional, a doctor, to say, okay, sorry madam, but you're not going to respond to this therapy, but think of it this way, that's a good thing, because now you don't have to suffer for this chemo, which is going to be pointless anyway. So from that perspective, a lot of these technologies that have been developed have already made it into the clinic. Once we understand these signals that tell us a little bit about, like I said, diagnosis and prognosis, they might help us to specify the treatment these patients will benefit from. For instance, if we can see a very complex network of signals being up and down regulated once a tumor is proliferating, we can then start, okay, this particular patient has signals X, Y, and Z being upregulated, and we could treat all these three signals, these molecular signals, together in the tumor, providing very efficient treatment. Well, how can you personalize medicine? Well, only if you know how a personal molecular profile looks like. And that is exactly what our technologies eventually reveal. The problem is that we find many signals that we don't understand yet. So from that perspective, there's a lot of fundamental research still needed. Once this fundamental research is completed, then the pharmaceutical industry might try and target these specific signals with new drugs. And that goes beyond my expertise, because then it moves from the fundamental molecular research into pharmaceutical research, where you take this fundamental information and translate it into new drugs and medication.
What are your hopes for cancer research?
What I see is that more and more we are understanding the complexity of life and the complexity of death. And My hope is that by understanding that complexity, we'll actually simply improve the quality of life of society. And that really, I think, is where this research we're doing now is contributing.
Cancer research has come a long way in the past 50 years. Thanks to fundamental and applied research, cancer is now more curable than ever. But we still have a long way to go to make treatments less invasive and tough on the patients. Hopefully, personalized medicine that researchers like Ron Heeren are doing the groundwork for will be the answer.